All right. This is handout 1210 warm up in the shared folder. And this is a warm up. So it's a free response problem. And you can use graphing calculator. And you should try it first on your own. Okay. And we've been seeing problems like this. And after you've tried it, then let's see what we'll do together. So the function g, it works for x is greater than or equals 0. They give you an initial condition. They give you the first derivative, which they would need to because they didn't give you the first function. They give you the second derivative, which they don't need to, but it's nice of them to do because we could have done that using the chain rule. Find all the values of x on the interval 0.12 to 1. Okay. So this is actually a problem that we I think we just had on our practice test. I wish the graph of G has a horizontal tangent line. So the work you need to show, the point breakdown. Well, I'm not going to talk about the points, but the work you need to show. Let's see. So we need to find a horizontal tangent line. A little band-aid now. Okay. Horizontal tangent. Well, to find a horizontal tangent, it means it's flat. It means its slope is 0. So you need to show work for, okay, let's set the slope equal to 0. Right? That's a point. If you don't write that, you lost a point, even if you're doing it. You at least write g prime equals 0. You don't need to write the sign part because it was named for you. So the way I'd find this is I would do sine of x plus 1 over x. And I go to the window and I go 0.12 to 1. And we could try zoom fit, which takes your x window and pre-calculates all the y's to adjust the y window. So there's the graph. And I mean, you don't need to draw this, but if you did, let's see, we're at 0.12 to 1. And the graph looks like that. Now it looks like it has one there and it has one here. So we're going to do second calculate 0. And I'm going to say, well, let's look at 0.12 to 0.2 and guess 0.19. Let's see if that works. 0.1634045. And notice it's not exactly 0, but -2 times 10 to the -13th is 12 zeros. And then the first number. So it's pretty small. Pretty much 0 for us. 12 zeros. 0 to 12 decimal places. Other one, so I can calculate 0. We can say this is our left bound. 0.5 is our right bound. 0.4 is our guess. 0.359433. I'm writing all this stuff on the graph. I'm not expecting any credit for anything I'm drawing over here. This is just to help me organize my thoughts and just in case I need it for something else later on. So those are your zeros. So the graph of G has a horizontal tangent line at x equals 0.163 and x equals 0.359 because g prime of x equals 0 at those points. So like I said, that was going to be worth a point, and then I think your answer is going to be worth a point. Okay, B. On what intervals 0.12 to 1, if any, is the graph of G concave down? So we're looking for concave down on 0.12 to 1. Justify your answer. Okay? Does that mean we say like second derivative test or something like that? No, that's nothing to do with concavity, concave down or up. It has to do with relative maximum min. So, but we are going to look at the second derivative. So we have the second derivative. I'm going to turn that graph off. I'm going to put this other graph in there, parentheses 1 minus 1 divided by x squared, close cosine of x plus 1 over x. I'm going to go window is the correct window. We could do zoom fit, graph the second derivative. So this is where you're using your calculator, because I don't think you want to try and solve these by hand. I don't think you're going to be able to. I don't know. So there's a graph. I'm just going to sketch it. So we have 0.12 to 1, and it looks like it crosses here and here. Be careful, because you might be like, oh, that looks like it crosses at 0.12, or you might even think that's 0 if you forgot that your window is 0.12. By the way, it might be interesting to graph these graphs from 0, and I think they do a lot of crazy stuff between 0 and 0.12. But let's let our calculator find these. First of all, is there an x-intercept there? Is there more than one? There's one there, obviously, find it. Is there another one between here and here, or does it approach the x-axis like an asymptote? Let your calculator verify that for you. Okay, don't need to even zoom in. So we're going to look for zeros. I'm going to look for one over on this far left side, 0.12 to 0.2, guess 0.13. So I'm making it look way over here, and it finds one. 0.1294578 which is different than 0.12. So I can calculate 0. I'm going to look for one over here. So I'm going to say, well, let's look for this one first, since we're over here. I don't feel as comfortable just entering numbers in. I feel like it's hard for me to tell. So this one is 0.222734280. And then let's make sure that there's not another one between here and the right side, 1. And our guess is going to be, 0.4. So it's going to start looking over here, and it's going to find the closest one. Oh, it might. Yeah. So it says there's a 0 at x equals 1. Oh, okay. Now, it does say on subinterval, on what subintervals of 0.12 to 1, so it doesn't include the endpoints. Okay, so we're going to say, now right here, this is positive. This is G del prime is positive. It's concave up for that little chunk. This is G del prime is negative, concave down. Now, anything I'm writing down in this picture, I'm not hoping to get credit for. So I just got to make sure to put this in word positive, concave up. So we're looking for concave down. So it's that one chunk. So we're going to say the graph I mean, you might even write a little note to yourself. Okay, we're looking for a negative second derivative, but we're going to put this all in words. The graph of g is concave down on 0.129, comma 0.222. Don't include the endpoints. Since g double prime of x is negative on the same interval. So I think a point for your answer and a point for your justification. C, write an equation for the tangent line to the graph of G. So we want equation of a tangent line to G at x equals 0.3. So we need a couple things. We need a point and a slope. Now the slope I think is pretty easy because we're going to plug 0.3 into our derivative, or you could even, write it out and then type it in. I did enter it in my calculator. I could use the table if I wanted. This is a quick calculation though. Sine of 0.3 plus 1 divided by 0.3 is negative 0.472161. That's a point for finding the slope. We need a point though. We have the x coordinate, but we need the y coordinate that goes with it. And we don't have the original y function. We don't have the original g function. We have the derivative. And so some people might be like, okay, well, let's integrate the derivative so we can try and, find this plus c, use initial condition, because it gave you, let's see, no. Oh yeah, they give you initial condition at the beginning of the problem that said g1 equals 2, right? So we're going to use that. The problem with this is you can't integrate this. Some people are like, oh, that's negative cosine x plus 1 over x. No, because there's this whole inner function and there's no way to just fix it. You guys actually cannot pull this off as an indefinite integral. But your calculator can do these as definite integrals. So what we want to do is use the fundamental theorem of calculus part 1. And we use this a ton in these kind of situations. Not that you have to write this, but I'm just writing it out as a little note to you. We use this a ton, and people they don't see the opportunities to use it. So the opportunity to use it here is that we have G prime, and we have a calculator that can integrate it on a definite interval, and we have an initial condition, and we want to find out the point. But we use this idea in a lot of other situations too. Let's say you have the graph of G prime, and you can actually find the area of chunks of it underneath its curve. You could use this idea here. Even if you had an equation that you can integrate by hand, if you have a calculator, it's going to be way faster and probably more correct. So we want to use the idea that if we integrate this, we will get G, but we're going to do a definite integral. We have 1 and we want 0.3. So I'm going to put 0.3 on the bottom and 1 here. So you want to use the point and the point you want to find. I generally like to put them lowest to highest because that's just how we usually think of integrating. And then you plug them in. So this is fundamental theorem of calculus part 1. It's not something to memorize. Integrals undo derivatives. Plug in the limits. Now, this is what we're trying to find. So we're going to write, okay, well, G.3 equals, so we're going to add this over here, subtract this over here. So I'm doing a little algebra in my head. You can show more work if you need to. And this is work you need to show. They're going to give you a point for using fundamental theorem of calculus part 1. You don't have to say it. You got to show the work for it. So G.3 equals G1 is 2. And we're going to do this on our calculator. And this is way faster than the other option some of you want to take. but can't. 2 minus math 9 sine of x plus 1 over x close comma x comma 0.3 comma 1, and we get 1.546007. So now we can write the equation of our tangent line. It's going to be y minus this y coordinate, 1.546, equals the slope, negative 0.472 times x minus 0.3. And I'm just leave it in point slope form. There's nothing that you need to do with it after that. D says, does the line tangent the graph at x equals 0.3, so that the equation we just found, does it lie above or below the graph of G for just a certain chunk? Because graphs can go up and down, so a tangent line might be below it, but then end up crossing and go above it at some point. So we're just interested in this chunk. So here's the deal. Tangent lines, if it's concave up, I wouldn't memorize this, just draw a picture. If it's concave up, tangent line will be below the graph for sure, where it's concave up. If it's concave down, the tangent line, just draw it, will be above the graph where it's concave down. So that's the idea we're relying on, and that's what we're going to need to talk about. But the thing we need to do is figure out, well, what's the second derivative from 0.3 to 1? Now, we just graphed it up here. I'm glad I drew it, so I don't have to redo this work. This was 0.22, so 0.3 is like right here to 1 is all positive second derivative. It's all concave up. So I'm going to say for 0.3 to 1, the tangent line to the graph at x equals 0.3 lies, so we're looking at this one right here, right? Lies below the graph of G, since G double prime is positive, G is concave up on the interval 0.3 to 1. Some people make a mistake and they find the second derivative at 0.3 by itself. That's not enough, because it's got to keep going from 0.3 all the way to 1 to be below the graph the whole time, because if the concavity just dramatically changes right after the tangent line, that's not true anymore. So you got to establish that it's concave up for that whole chunk that we're answering for. That's it.